The Henderson-Hasselbalch equation is used to tell us how to prepare a buffer solution with a given pH. It's kind of a shorthand way to calculate the pH when you have a buffer solution. It really is just the same thing as if we were to go longhand and write out the dissociation of our generic weak acid HA breaking up into the hydrogen ion and its conjugate base A-. We would say Ka is equal to the concentration of the hydrogen ion times the concentration of the weak base A- all over the concentration of our weak acid. So we could still use this longhand way of figuring out pH and solving for the hydrogen ion concentration. The Henderson-Hasselbalch equation takes this and rearranges it into a nice useful format. So we end up with the pH is equal to the pKa of the weak acid plus the log of the concentration of the conjugate base over the concentration of the weak acid. So it's going to be the log of that entire fraction there. And that will give us the pH of that buffer solution. Now let's see how we could use that Henderson-Hasselbalch equation to quickly calculate the pH of a buffer solution. We have a 0.6 molar ammonia and 0.4 molar ammonium chloride solution, and that would mean that the NH3, our ammonia, would represent the base, and ammonia's conjugate acid is the ammonium ion, NH4+, so that would represent the weak acid. Now, in order to have a buffer, you have to have some concentration of a weak acid present with its conjugate base or a weak base present with its conjugate acid. With the ammonium chloride, the chloride anion is neutral, so we're just focusing on the ammonium cation part of this. So using Henderson-Hasselbalch, we can say that the pH of the solution can be calculated by taking the pKa, and that would be for our weak acid, plus the log of the concentration of our base over the concentration of the acid. So if we look up the Ka for the acid component, which is NH4+, the Ka off of our chart is 5.6 times 10 to the negative 10th. And if we want to calculate the pKa, we would take the negative log of the Ka. Anytime we take the pH or POH, pKa, we take the negative log of whatever that is. So the pKa for the ammonium ion comes out to being 9.25. So when we want to calculate the pH of this buffer solution, we're going to plug in that pKa, 9.25, plus the log of the concentration of our conjugate base, which we were told the ammonia was 0.6 molar. So we're going to plug in 0.6 molar on the top over the concentration of the weak acid. We had 0.4 molar ammonium. So we're going to plug in 0.4 in the denominator. And that gives us a pH of our buffer solution of 9.43. So this is really a quick shorthand way to figure out the pH of a buffer solution, and it's already taking into account that we often ignore X's that are added or subtracted when dealing with weak acids and weak bases because their Kas and Kbs are so small. We learned that buffers are able to absorb a certain amount of acid or base and keep the pH of the solution relatively constant. Buffers have a capacity though, and if you exceed their capacity, you can break the buffer. So a buffer capacity is essentially the amount of acid or base that a buffer solution can absorb without changing the pH significantly. Once that pH changes significantly, then we've essentially broken the buffering capacity of the solution. So if we look at the pictures on the right here, in this first one, the pH is measured at 8 of our buffer solution. And then we can imagine what would happen if we start adding some strong acid to it. If we add a bit of strong acid to our buffer solution, some of that strong acid can be absorbed by reacting with the conjugate base portion of the buffer. And we notice in the second picture, the pH has dropped from 8 down to 7.66. Well, now imagine we add a whole bunch of strong acid to our buffer solution. We can see here that the pH in the last picture has dropped all the way down to 1.53, and the color has changed of the universal indicator to red, indicating that the solution is now very acidic. So essentially, we've added so much strong acid that the buffer capacity has been exceeded for our initial buffer solution, and it's no longer keeping that pH relatively constant anymore. This image shows us what would happen if we added a strong acid or a strong base to pure water. So if we look at on the x-axis, that represents the volume of HCl, which is a strong acid, being added to water, and on the y-axis, we have the pH of the solution. So initially, our pH of neutral water hits right around that 7 or neutral mark. And then immediately upon any addition of strong acid, the pH falls all the way down to about 1.8, and then it drops all the way down to about 1.0. So a strong acid immediately changes the pH of water to very, very low pH numbers. And the exact opposite is true for if we were to add a strong base, such as sodium hydroxide, to a water solution. We would have initially a pH of 7 for our pure water, and then immediately upon adding just a couple drops of a strong base, the pH jumps up to around 12 and then eventually evens out at around 13. So there's no buffering capacity to something like pure water. This is not what would happen if we had a solution of a weak acid with its conjugate base. The buffering capacity of a buffer will depend directly upon the moles of weak acid and the moles of conjugate base present. So essentially that fraction or that ratio of moles of acid to moles of base. And what we see by looking at the graph on the right is that the more concentrated the buffer solution is, the greater buffering capacity it will have. So on the first one, we have distilled water, which we looked at on the previous slide, followed by 0.01 molar buffer solution. And that took about approximately 10 milliliters for that buffer to break. And then we move on to 0.025 molar buffer solution. And that one took maybe about 25 milliliters for that buffer to break and the pH to shoot up. And moving on to an even more concentrated buffer, 0.05 molar, 0.1 molar, all the way up to 1 molar. All three of those buffers really were not even broken all the way at 40 milliliters of our strong base being added. So the more concentrated buffers work better than the less concentrated buffers at being able to absorb either strong acid or strong base. Many biological applications actually need a solution to buffer at a very specific pH. So we can design a buffer system to actually buffer at a certain pH and remain relatively close to that value. By selecting a weak acid where the pKa of that weak acid is very close to the desired pH that we want to buffer at, we can then slightly adjust that ratio of weak acid and conjugate base to create a buffer system that will buffer at a very specific pH. Which of the following mixtures is most appropriate for buffering a solution with a pH of 3.45? A, we have a sodium fluoride hydrofluoric acid buffer. B, we have a nitrous acid sodium nitrite buffer. And C, we have a hypochlorous acid sodium hypochlorite buffer. So in each one of these, we have a weak acid paired up with its conjugate base, and next to them, the Ka for the weak acid component is written down. So the Ka for the sodium fluoride hydrofluoric acid buffer system is 7.2 times 10 to the negative fourth. By taking the negative log of that, we can calculate the pKa, and the pKa comes out to 3.14. For B, we have a Ka for our nitrous acid of 4 times 10 to the negative fourth, so the pKa comes out to being 3.39. And for C, for our hypochlorous acid, the Ka is 3.5 times 10 to the minus 8. And if we calculate the pKa, we end up getting 7.45. So we want to buffer around pH 3.45. So the combo of the weak acid and conjugate base that gives us a pKa closest to the pH will be the correct pair for our application. So in this case, the best choice would end up being B, our nitrous acid sodium nitrite combination, because the pKa was 3.39, and that's closest to the desired pH. Next, we can learn how we figure out the ratio of weak acid to conjugate base in order to buffer at a specific pH. So in this example, we're using an acetic acid and sodium acetate combination, and we want to buffer at pH of 5. So we can use Henderson-Hasselbalch to make this an even shorter problem. The pH will equal the pKa plus the log of our conjugate base over our weak acid. And essentially, we're going to want to figure out what that fraction is of our ratio of our conjugate base to our weak acid right here if we want to know what our ratio of those have to be. So the pH we're told we want to buffer at is 5. And our pKa for our weak acid, we're going to have to calculate that. The Ka for acetic acid is 1.8 times 10 to the negative 5th. And we can take the negative log of that to calculate the pKa. So the pKa is 4.74 for acetic acid. So we'll have 4.74 that we plug in, plus the log of our base over our acid. So if we subtract our pKa from our pH to isolate our ratio, that would give us 0.26. And that will be equal to the log of our base concentration over our acid concentration. And in order to get rid of that log term, we're going to have to take 10 to both sides. So we'll end up getting 10 to the 0.26, and that will get rid of the log term on the right, and that will be equal to the concentration of our base over our acid. So 10 to the 0.26 power gives us 1.82. And that doesn't look like it's written as a ratio, but we can assume that that number is over 1. We can take any number and write it over 1. So that tells us essentially that we need 1.82 moles of our base, which our base in this example was the acetate anion, C2H3O2-, to every 1 mole of our weak acid, which is acetic acid. And that would tell us exactly how many moles we need in order to buffer at that exact pH of 5.0. So this would be actually our answer. Let's try another buffer example. How would you prepare a sodium carbonate buffer solution that has a pH of 10.40? So our sodium bicarbonate must be our acid component, and the sodium carbonate must be our base. Sodium bicarbonate has a proton in it, which makes it able to be an acid. So that will be our acid conjugate base pair. The sodium is just a spectator ion, and the anion portion is serving as the acid or base. So our Ka for our bicarbonate ion, we can look up on our chart, and that's 4.8 times 10 to the negative 11th. And we can take the negative log of that to get the pKa for our acid, and that comes out to about 10.3. Notice that this acid-base pair was chosen in the first place to start with because the pKa of the acid is very close to the pH which is being buffered at. So from there we can tweak it a little bit more to get it to be close to our desired pH by adjusting the moles of acid to moles of base. So using Henderson-Hasselbalch, pH equals pKa plus the log of the concentration of our base over the concentration of our acid, just for shorthand notation. And we can plug in our pH that we're desired to buffer at, 10.40. And our pKa was 10.3 plus the log of our base over our acid. If we subtract our pKa from our pH, that gives us 0.10 equal to the log of the concentration of our base over our acid. And then we're going to have to take 10 to both sides to undo our log. We'll end up with 10 raised to the 0.10 power equals our ratio of base to ratio of acid. And that will give us a number, 1.26, and we can imagine that to 1. So if we took 1.26 moles of our base component, which is CO3 2- carbonate anion, to 1 mole of HCO3 minus, the bicarbonate ion, and we dissolved both of those in 1 liter of solution, that would give us a buffer solution that will buffer specifically at 10.40. So this tells us the ratio of those moles per 1 liter of solution.